September 10, 1943. Over the fields of Sicily, 4,200 feet above enemy territory, a Canadian pilot named Lieutenant Thomas Weber crouched behind a reconnaissance camera inside the cramped fuselage of a Westland Lysander. The engine coughed in the thin morning air. Below him, German flak batteries tracked his slow-moving silhouette against the pale Mediterranean sky. The first burst came without warning. Black flowers bloomed in the air 30 yards to starboard. Weber pressed the camera trigger. The shutter clicked. The film advanced. Another burst closer this time. The aircraft shuddered. Metal fragments punctured the fabric covering on the left wing. He kept the camera running. Standard procedure required 3 overlapping photographs of the target zone. He had taken one. The whistle came before the explosion. Sharp, rising, inevitable. Weber braced. The shell detonated 40 feet below the tail section. The Lysander pitched forward. The camera mount broke loose. Weber grabbed it with both hands, steadying the lens while the pilot fought for control. One more photograph. Just one more. The shutter clicked again. The screen in his mind went black. Before satellites scanned continents from orbit, before remote eyes circled above battlefields, recording everything, risking nothing, there were men who flew into enemy fire for a single photograph. Men who understood that intelligence won wars, that knowing where the enemy slept could save 1,000 lives, that reconnaissance was not glory but geometry, cold angles, calculated risk, blood traded for information. Lieutenant Weber survived that morning. His aircraft did not. The photographs he captured showed German artillery positions near Gela with enough clarity to direct naval bombardment 3 days later. The intelligence officer who developed the film counted 27 bullet holes in the fuselage. Weber received a commendation. 6 weeks later, over the coast of Italy, he disappeared. No wreckage found. No body recovered. Just another name added to the casualty lists that grew longer every month. But one man in Ottawa believed there was another way. A way to see without being seen. A way to gather intelligence without gambling human lives against enemy guns. He was not a pilot. He had never flown in combat. Poor eyesight disqualified him from service. Yet he understood something fundamental about aerial reconnaissance that even the most experienced pilots had not yet grasped. The camera did not need the man. He called it a flying eye. A remote-controlled aircraft capable of photographing enemy positions from distances that made anti-aircraft fire irrelevant. In 1942, when the concept of unmanned flight existed only in science fiction magazines and engineering journals, he built a prototype in an unheated hangar using salvaged parts and borrowed equipment. The military establishment dismissed it as impractical. The Air Ministry refused funding. His superiors ordered the project terminated. He continued anyway. What happened in that Canadian hangar between 1942 and 1943 represented more than technical innovation. It represented a fundamental reimagining of warfare itself. The idea that observation could be separated from risk, that machines could bear the burden of reconnaissance while men remained safely beyond the reach of enemy fire. That technology could reduce the terrible arithmetic of war, where every photograph cost blood, every intelligence report demanded sacrifice. The man's name was Reginald Clarke, 34 years old, electrical engineer at Canada's National Research Council. Modest, methodical, unknown. He worked alone most nights, tinkering with radio frequencies and gyroscopic stabilizers while snow drifted against the hangar walls. His colleagues thought him obsessive. His supervisors considered him insubordinate. History would eventually recognize him as a pioneer of unmanned aerial reconnaissance. Though that recognition would come decades too late, long after his death, buried in archived files that few would ever read. This is the story of how one quiet engineer's impossible idea made reconnaissance safer for Allied troops, how persistence defeated bureaucracy, how a machine built from scrap metal and stubborn determination proved that wars could be fought with fewer casualties. That observation did not require martyrdom, that the future of aerial intelligence belonged not to brave men in fragile aircraft, but to eyes without bodies, cameras without coffins. It begins not with triumph, but with crisis, not with innovation, but with catastrophe. Because the idea that would eventually save lives was born from the realization that too many had already been lost. In the early years of World War II, aerial reconnaissance was both vital and deadly. Every major operation depended on it. The Dieppe raid in August 1942 required precise beach gradient measurements. The Sicily invasion in July 1943 demanded harbor depth surveys. Planning for Normandy consumed thousands of reconnaissance photographs. Planners needed to know gun positions, troop concentrations, radar installations, supply depots, bridge load capacities, road widths, forest density. They needed measurements accurate within meters. They needed updates every 48 hours. The aircraft that provided this intelligence flew unarmed, low and slow. Westland Lysanders cruised at 165 miles per hour, maximum altitude 21,000 feet, range 600 miles. Designed for observation, not survival. The cockpit sat exposed canvas and aluminum protection measured in millimeters. Pilots flew alone or with a single observer, cramming behind manual cameras that weighed 47 pounds and required constant adjustment for altitude, light, and vibration. Each mission meant penetrating enemy airspace at speeds that made them easy targets for both fighters and anti-aircraft batteries. Spitfire PR variants flew higher and faster, but carried limited fuel and smaller cameras. The Mosquito PR IX offered speed and range but remained rare, expensive, reserved for deep penetration missions over Germany. Most tactical reconnaissance fell to older aircraft, slower platforms, machines that traded protection for payload. The cameras required stable flight. Stable flight required predictable patterns. Predictable patterns meant German gunners knew exactly where to aim. Casualty rates told the story in numbers that made headquarters uncomfortable. RAF photo reconnaissance units reported losses averaging 18% per month during 1942. 1 in 5 pilots never returned. RCAF reconnaissance squadrons operating from Britain calculated similar figures. Over France, over the Low Countries, over Norway, young men flew straight lines through flak fields because the camera needed 3 overlapping images, and overlapping images required maintaining course despite the black flowers blooming around them. The arithmetic was brutal and simple. Intelligence required photographs. Photographs required aircraft. Aircraft required pilots. Pilots died. The equation demanded bodies. Command accepted this as the price of modern warfare, the cost of knowing what lay beyond the horizon. But the cost kept rising. Camera technology made the problem worse. The standard F-24 reconnaissance camera used in RAF aircraft recorded images on 5-inch film, required manual operation, suffered from vibration blur at low altitudes, and provided no confirmation of image quality until the film was developed hours after landing. Missions failed because the camera jammed. Missions failed because clouds obscured the target. Missions failed because the pilot dodging flak banked 3 degrees too steep and ruined the exposure. The film canister might contain perfect intelligence or blank frames. No one knew until the chemicals revealed truth or failure in the darkroom. Weather compounded everything. Reconnaissance required clear skies. Cloud cover made photography impossible. Missions launched, flew deep into enemy territory, returned with nothing because fog rolled in at the wrong moment. Pilots risked their lives for blank film. The waste frustrated everyone. Operations officers, pilots, photo interpreters who spent hours examining useless images, trying to extract intelligence from blur and shadow. The human cost exceeded statistics. Each loss meant training, wasted experience gone, institutional knowledge erased. Training a reconnaissance pilot took 8 months. Teaching him to read terrain, judge altitude without instruments, maintain course under fire, estimate, wind drift, operate cameras, while flying took another 4 months in operational squadrons. A single pilot represented a year of investment. German flak batteries destroyed that investment in seconds. Lieutenant James McLeod disappeared over Brest in October 1942. 22 years old, 16 missions completed, excellent photographer, calm under fire. His Lysander went down near the harbor. No parachute observed. The photographs he died attempting to capture showed German submarine pens already documented in previous missions. The intelligence officer who reviewed McLeod's mission report wrote 3 words in the margin: unnecessary, redundant, preventable. Flying officer Patricia Wilson, one of the few women flying reconnaissance for the Air Transport Auxiliary, ferried damaged Spitfires from reconnaissance units back to maintenance depots. She saw the bullet holes, the shredded control surfaces, the blood stains in cockpits. She counted aircraft that returned versus aircraft that departed. The mathematics haunted her. Every third sortie produced a casualty. Every fifth mission cost a life. The numbers were not sustainable. The strategic situation created impossible pressure. Allied planners needed more intelligence, more photographs, more updates. German defenses grew stronger. Flak batteries multiplied. Luftwaffe fighters adapted tactics, specifically targeting slow reconnaissance aircraft. The reconnaissance squadrons flew more missions with fewer pilots. Exhaustion became a factor. Fatigue killed as surely as enemy fire. Pilots made mistakes in the 200th hour that they never made in the 20th. Something had to change. The current system was consuming men faster than training could replace them. The photographs were becoming more expensive than the intelligence they provided. Operations officers began questioning whether certain missions justified the risk, whether knowing the exact position of a supply depot was worth a pilot's life, whether redundant surveillance made tactical sense when the cost was measured in coffins. Somewhere in Ottawa, a quiet electrical engineer named Reginald Clarke read casualty reports and wondered if there was another way, not a better way to train pilots, not improved armor for aircraft, not faster cameras or clearer film, something more fundamental, something that would eliminate the human element entirely from the most dangerous phase of reconnaissance. What if the camera could fly without the pilot? Reginald Clarke was 34 years old when he decided to build an aircraft that could fly without a pilot. He stood 5'8", weighed 148 pounds, wore wire-rimmed glasses that constantly slipped down his nose, and possessed the kind of quiet intensity that made colleagues uncomfortable. He rarely spoke in meetings. He never raised his voice, but when he committed to an idea, he pursued it with a focus that bordered on obsession. He worked at Canada's National Research Council in Ottawa, a sprawling complex of laboratories and workshops where engineers developed radar systems, improved aircraft instruments, and tested communication equipment for the war. Effort. Clarke's official assignment involved radio frequency calibration for naval vessels. Routine work, necessary but unglamorous. He completed his assigned tasks by early afternoon, then disappeared into Hangar 7, a drafty outbuilding at the edge of the facility, where obsolete equipment gathered, dust and forgotten projects died quietly. Nobody questioned what he did there. Clarke had earned a reputation as a tinkerer, the kind of engineer who salvaged broken radios for parts, who repaired instruments other technicians had abandoned, who spent evenings sketching circuit diagrams in notebooks he never showed anyone. His supervisors tolerated the eccentricity because his official work was flawless. Precise calibrations, thorough documentation, zero errors. What he did after hours was his business, provided it didn't interfere with essential projects. He couldn't fly. The Royal Canadian Air Force rejected his application in 1940. Visual acuity below minimum standards. His left eye measured 20/40, even with corrective lenses. Depth perception slightly impaired. The medical officer had been apologetic. "We need every man we can," the officer said, "but we can't put someone in a cockpit who might misjudge altitude in combat." Clarke had nodded, thanked him for his time, walked out of the recruitment office into cold October rain, feeling ashamed of his own biology. But he understood aircraft, not from flying them, but from studying how they worked. Radio systems, control surfaces, gyroscopic stabilization, signal propagation. He had worked as a radio technician throughout the 1,930 first for commercial broadcasting stations, then for the Department of Transport, installing navigation beacons across northern Ontario. He knew how radio waves behaved at altitude. He knew how to transmit control signals across distances. He knew theoretically how to make an aircraft respond to commands sent from the ground. The idea had existed in his mind for years, dormant, theoretical, impractical. Remote control worked for small devices. Model aircraft hobbyists in Britain and America had demonstrated radio-controlled gliders before the war. But scaling the technology to military reconnaissance aircraft seemed impossible. The weight of radio equipment, the complexity of control systems, the unreliability of signal transmission under combat conditions. The problems multiplied faster than solutions. Then his brother died, Flight Lieutenant David Clarke, 28 years old. Reconnaissance pilot flying Spitfire PR variants out of RAF Benson in Oxfordshire. 17 missions completed. excellent photographer, steady under pressure. On February 14th, 1941, he took off on a routine surveillance mission over the French coast near Calais. Weather clear, visibility good, expected return time 1,600 hours. He never came back. The telegram arrived 3 weeks later, missing in action, presumed killed, no witnesses, no wreckage recovered. Just another name on a casualty list that grew longer every week. Reginald Clarke read the telegram twice, folded it carefully, placed it in his desk drawer, and walked to Hangar 7. He didn't cry. He didn't rage. He sketched. By midnight, he had filled 6 pages with diagrams, radio control systems, gyroscopic autopilots, camera mounts, recovery mechanisms. By dawn, he had calculated theoretical range and payload capacity. By the end of the week, he had written a 12-page proposal titled Remote Aerial Observation System. He submitted it through proper channels. The NRC Review Board met 3 weeks later. Their response came in a single paragraph. Impractical for current operational requirements. Insufficient funding available. Recommend focus on approved projects. Clarke filed the rejection letter next to his brother's telegram. Then he started building anyway. He scavenged parts from damaged training aircraft awaiting disposal. Wooden propellers with repairable cracks. Aluminum tubing salvaged from wrecked gliders. Fabric covering torn but usable. Radio components from obsolete naval equipment. Nobody tracked these materials closely. The war produced enormous waste. Damaged equipment piled up faster than salvage crews could process it. Clarke simply accelerated the process, redirecting certain items to Hangar 7 before they reached official disposal. 2 junior mechanics named Thomas Bright and Robert Cheswick joined him. Both had been rejected for flight training. Bright, due to chronic air sickness. Cheswick, because of partial hearing loss in his right ear. They worked unpaid after hours, motivated by the same quiet fury that drove Clarke, the belief that better technology could reduce casualties. That machines could bear risks instead of men. That engineering could save lives if given the chance. Winter 1942 brought brutal cold to Ottawa. Hangar 7 had no heating. They worked in overcoats, their breath visible in the dim light from single overhead bulbs. Clarke's hands went numb, handling metal components. Bright developed frostbite on 3 fingers. Cheswick caught pneumonia and missed 2 weeks. They continued anyway. The first airframe took shape slowly. A simple high-wing monoplane design, wingspan 12 feet, fuselage 8 feet long, constructed primarily from plywood and spruce. Weight mattered. Every ounce of radio equipment reduced payload capacity. Every pound of structure meant less range. Clarke calculated obsessively, trimming weight wherever possible, searching for the perfect balance between durability and efficiency. He called it Project OWL, Observation Wireless Liaison. The name appeared in his notebooks, written in careful block letters above technical specifications and flight projections. Nobody at NRC knew the project existed. His supervisors assumed he was still tinkering with radio equipment. His colleagues thought he was working on personal hobbies. None of them imagined he was building Canada's first remotely piloted aircraft in an unheated hangar using stolen parts and borrowed time. He couldn't fly, but he could make something fly. And if it worked, if the mathematics proved sound, if the radio systems functioned as designed, then maybe other brothers wouldn't disappear over France. Maybe other mothers wouldn't receive telegrams. Maybe reconnaissance could happen without coffins. Late nights in Hangar 7, Clarke stood before his half-built aircraft and spoke to the silence. If a machine can steer itself, he said quietly, then a man need not die to see what's on the other side of the hill. The machine didn't answer, but slowly, impossibly, it was beginning to take shape. August 19th, 1942. Dawn broke over the French coastal town of Dieppe. At 0507 hours, Canadian troops from the 2nd Division hit the beaches. By 0900 hours, the operation had become a catastrophe. Of the 6086 men who landed 3367 became casualties, dead, wounded, or captured. The highest single-day loss rate Canada suffered in the entire war. The intelligence had been flawed. Reconnaissance photographs showed the beach gradient as suitable for Churchill tanks. The photographs lied. Tanks bogged down in loose shale, unable to climb the seawall, becoming stationary targets for German guns. Photographs suggested limited coastal defenses. The photographs missed reinforced concrete bunkers concealed in cliff faces. Photographs indicated clear routes inland from the beach. The photographs failed to reveal anti-tank obstacles buried beneath the surface. Men died because cameras missed details, because film couldn't penetrate camouflage, because reconnaissance aircraft flying at 8,000 feet couldn't distinguish between gravel and shale, because the intelligence that generals used to plan operations was incomplete, outdated, fatally inadequate. Reginald Clarke read the casualty reports in the Ottawa Citizen on August 21st. He read the lists of names: Royal Regiment of Canada, Essex Scottish, Royal Hamilton Light Infantry, South Saskatchewan Regiment, boys from small towns, farm kids, factory workers, dead on a French beach because someone didn't know the exact gradient of the shale. He thought about his brother, reconnaissance pilot, dead over France gathering photographs just like the ones that failed at Dieppe. He thought about all the missions flown, all the pilots lost, all the photographs that still couldn't answer the questions that mattered. How hard is the beach surface? How thick is the concrete? Where exactly are the guns positioned? The photographs had been blurred, the targets misjudged, the cost measured in lives. Clarke sat in his small apartment that night, surrounded by technical drawings for Project Owl, and felt the weight of every name in those casualty lists. His design wasn't ready, his prototype wasn't complete. But it existed, a machine that could fly lower, slower, longer than any manned aircraft. A camera platform that could loiter over targets, take multiple photographs from different angles, return or self-destruct without risking human life. If it had existed 6 months earlier, maybe Dieppe would have gone differently. Maybe reconnaissance would have revealed the true beach conditions. Maybe Canadian boys would still be alive. September 1942. Clarke requested a formal meeting with NRC senior administrators. He brought technical specifications, flight projections, cost estimates, weight calculations, radio frequency diagrams, everything necessary to demonstrate feasibility. The meeting lasted 14 minutes. Impractical, the chief administrator said. The radio equipment alone weighs more than most reconnaissance cameras. How do you propose to lift that weight with an unmanned aircraft? Clarke explained gyroscopic stabilization, weight reduction through simplified control systems, the elimination of cockpit instruments. The administrator interrupted. "We're focused on radar development," the man said. "That's where resources go. Radio-controlled toys don't win wars." Clarke tried again in October. The Air Ministry liaison officer stationed at NRC listened politely to his presentation. "Fanciful," the officer concluded. "The Royal Air Force needs operational systems, not experimental concepts. We have reconnaissance aircraft. We need better cameras, better film, better photo interpretation, not remote control systems that might work in perfect conditions." "What about casualties?" Clarke asked. "What about the pilots we're losing every week?" The officer's expression hardened. "We're all making sacrifices," he said. "That's what war demands. Your job is radio calibration. I suggest you focus on that." November brought official termination. A memorandum arrived from NRC headquarters. Project Owl unauthorized. Use of facility resources without approval constitutes misappropriation. All work will cease immediately. Materials will be returned to inventory. Clarke read the order 3 times. Then he walked to Hangar 7 and locked the door from the inside. Thomas Bright and Robert Cheswick found him there an hour later, sitting on the concrete floor beside the half-completed airframe. "They're shutting it down," Clarke said quietly. "Orders from headquarters. Official, binding, we're done." Bright and Cheswick looked at each other. Bright spoke first. "So we stop building during work hours. We stop using official materials. We stop asking permission." Cheswick nodded. "We build anyway," he said. "Nights, weekends, our time, our choice." Clarke looked up at them. "This could cost you your positions, insubordination, misuse of facilities. They could terminate you." Bright shrugged. "They can fire us for building a machine that might save lives," he said. "I'll take that risk," Cheswick agreed. "My cousin died at Dieppe," he said. "I'd rather get fired trying to prevent another Dieppe than keep my job doing calibration checks." Clarke stood slowly. "Rules were made in offices," he said quietly, "but wars are lost in the field. If we stop now, nothing changes. If we continue, maybe we build something that matters," they continued. December 1942 through February 1943 became a study in calculated defiance. Clarke signed out radio components under false requisition codes, equipment for naval frequency testing, actually destined for aircraft control systems. Bright acquired aluminum tubing through a friend at a civilian aircraft repair facility. Trade arrangements, favors exchanged. Nothing technically illegal, but nothing exactly authorized either. Cheswick bartered for gyroscopic instruments from a merchant marine salvage yard, damaged navigation equipment from torpedoed freighters, repairable if you knew what you were doing. They worked at night, when Hangar 7 sat empty and dark. Clarke installed blackout curtains so light wouldn't attract attention. They arrived separately, left at different times, never discussed the project during daylight hours, never left documents visible. The airframe slowly took shape in absolute secrecy, a ghost project, officially terminated, practically unstoppable. Clarke's guilt about Dieppe became fuel. Every night he spent in the freezing hangar felt like penance. Every part he installed felt like memorial. He wasn't building a reconnaissance drone. He was building a promise, a commitment that future operations would have better intelligence, that future soldiers wouldn't die because photographs missed crucial details, that machines would bear the risk instead of men. Winter storms hammered Ottawa. Snow piled against the hangar walls. Wind screamed through gaps in the corrugated metal siding. Clarke's hands cracked and bled from handling frozen metal. Bright developed a persistent cough that wouldn't quit. Cheswick's hearing got worse from prolonged exposure to cold. None of them stopped. By March 1943, the airframe was complete. 12-foot wingspan, 8-foot fuselage. Plywood construction reinforced with aluminum struts. Empty weight 42 pounds. Radio control system installed. Gyroscopic stabilizer mounted. Camera attachment points ready. Everything functional, everything designed, everything unauthorized. Clarke stood in the cold hangar on March 15th alone, looking at what they'd built. Wind howled through the darkness outside. The prototype sat on makeshift sawhorses, unpainted, raw, impossible. A flying eye. A machine that could scout without dying. A refusal to accept that reconnaissance required sacrifice. He touched the propeller gently, solid wood, perfectly balanced, ready to spin. Time for the impossible part, he said to the empty air. Time to make it fly. May 8th, 1943. Rural airfield near Rockcliffe, Ontario. 0547 hours. Temperature 41 degrees Fahrenheit. Wind southwest at 8 knots. Clear skies. Perfect conditions for what Reginald Clarke was about to attempt. The prototype sat on the grass runway, unpainted plywood, reflecting early morning light, 12-foot wingspan, 42 pounds empty weight, 63 pounds loaded with radio equipment and camera, single-cylinder engine salvaged from a damaged training glider, wooden propeller hand-carved by Thomas Bright during February nights in the freezing hangar, radio receiver mounted behind the engine cowling, gyroscopic stabilizer positioned at the center of gravity, 16mm cine camera secured on shock absorbers beneath the fuselage. No military clearance, no official observers, no documentation. Just 3 men, a machine, and an idea that could redefine reconnaissance. Clarke knelt beside the aircraft, performing final checks. Control surfaces responded to radio commands. Elevator, rudder, ailerons. Each movement smooth, precise, immediate. The radio transmitter sat 50 yards away on a folding table. Modified naval torpedo guidance system. Range theoretically 5 miles. Actually untested beyond 300 yards in the hangar. Everything was theory now. Mathematics and hope. Robert Cheswick primed the engine. 3 pulls. The propeller caught. The engine coughed once, settled into rough idle. Vibration shook the airframe. Clarke watched the camera mount, checking for excessive movement. The shock absorbers held. The lens remained steady. Good enough for government work, Cheswick said quietly. Good enough to prove concept, Clarke replied. Bright manned the radio transmitter. Launch checklist memorized. Engine full throttle on command. Monitor altitude response. Correct drift immediately. Maintain visual contact. Recovery by parachute deployment at programmed altitude. Simple in theory. Catastrophic if any single component failed. Clarke stepped back. His hands were shaking. Not from cold. From the knowledge that everything he'd built, everything he'd risked, everything he'd sacrificed over 18 months came down to the next 3 minutes. Either the aircraft flew under radio control, or it didn't. Either the concept worked, or he'd wasted government resources on an elaborate fantasy. Either machines could scout without pilots, or Reconnaissance would continue consuming men until the war ended. "Launch when ready," Clarke said. Bright advanced the throttle. The engine screamed. The propeller became invisible blur. The aircraft rolled forward, picking up speed across grass still wet with morning dew. 10 feet, 20 feet, 30 feet, the tail lifted, the wings generated lift. Airborne. For 5 perfect seconds, Project Owl flew straight and level. Then physics and inadequate engineering met reality. The aircraft veered left, hard, 30 degrees off centerline. Bright overcorrected on the radio controls. The aircraft banked right overcorrected, entered a spiral. The gyroscopic stabilizer couldn't compensate fast enough. The radio signal lagged 0.3 seconds behind control input. 0.3 seconds at 70 miles per hour meant disaster. Altitude 50 feet and climbing. Bright fought the controls. The aircraft responded, but wrong, always half a second behind where it needed to be. Clarke watched his 18 months of work spiral across the morning sky. "Cut the engine," he shouted. "Bring it down now." Bright killed the throttle. The propeller windmilled. The aircraft descended in a flat spin, still banking, still uncontrolled. It hit the ground 300 yards from launch position. The impact sounded like kindling snapping. Plywood shattered. The engine tore free from its mounts. The tail section broke clean off. Silence followed. Then smoke. Then the sharp chemical smell of burning insulation. Clarke ran. Cheswick and Bright followed. They reached the wreckage in 40 seconds. The airframe was destroyed. Total loss. Months of work scattered across grass and splinters and torn fabric. The engine smoldered. The radio equipment sparked and died. The gyroscope had broken free, rolled 15 feet away, bent beyond repair. Clarke knelt in the grass. He didn't speak, didn't curse, didn't move. Bright stood behind him, breathing hard. Cheswick circled the wreckage, cataloging damage, already calculating what could be salvaged. Then Clarke noticed the camera. It had separated on impact. The shock absorbers worked exactly as designed, protecting the mechanism, even as the aircraft disintegrated around it. The camera lay in grass 10 feet from the main wreckage. Lens intact. Housing dented but sealed. Film canister secure. Clarke picked it up carefully. The mechanism was warm, still functional. He opened the back panel with shaking hands. The film reel sat undamaged. 16 millimeters of celluloid that might contain proof of concept or might contain nothing but blur and sky. "We need to develop this," he said quietly. "Now." They drove back to NRC headquarters in silence. Clarke carried the film canister like a sacred object. Bright drove. Cheswick sat in the back seat, already sketching modifications for the next prototype. Stronger airframe, faster gyroscope response, reduced radio lag. The crash hadn't discouraged him. It had provided data. The photography lab at NRC was empty. Weekend. Skeleton staff. Clarke had credentials. He signed in, took the film to a development room, locked the door. Cheswick and Bright waited outside. Processing took 40 minutes. 4 minutes of flight. 40 minutes to discover if it meant anything. Clarke emerged holding a strip of developed film up to the light. Bright saw his expression and knew immediately. "You got something," Bright said. "Not a question. A statement." Clarke nodded slowly. 6 frames, blurred but recognizable. The airfield from altitude. Trees, grass. The horizon line perfectly level in the 3rd frame. Focus soft but sufficient. Proof that a camera mounted on a remotely piloted aircraft could capture usable imagery. Proof that the concept worked. The crash didn't matter. The destroyed prototype didn't matter. These 6 frames of film mattered. Evidence that machines could observe enemy territory without pilots, that reconnaissance could happen at distances that made anti-aircraft fire irrelevant, that perhaps finally intelligence gathering might stop consuming lives. Clarke held the film strip carefully. For the first time in 18 months, he smiled. "We need to fix the control lag," he said. "The gyroscope needs faster response time. The airframe needs structural reinforcement at the wing roots." Bright nodded. "I can have a new frame built in 2 weeks. Cheswick added, "I know where to get better radio components. Commercial aviation salvage in Montreal. Not military spec, but faster response than the torpedo guidance system." They rebuilt through May and June. Longer wings for stability. lighter airframe for reduced weight, faster gyroscope borrowed from British Admiralty torpedo designs, radio system completely redesigned, reduced lag to 0.1 seconds, still not perfect but survivable. July 17, 1943. Same airfield, same conditions, different aircraft. Clarke had learned from failure. The new prototype incorporated every lesson from the May crash. Reinforced structure, improved controls, faster response, better balance, launch at 0612 hours, engine throttle advanced, aircraft rolled, lifted, climbed. This time it held course. Bright managed the controls from the ground station. The aircraft banked gently left, responded, banked right, responded, climbed to 200 feet, held altitude. The gyroscope worked. The radio lag was manageable. The airframe remained stable. 4 minutes of controlled flight over the Ottawa River Valley. The camera clicked continuously. 16 frames, 32 frames, 48 frames. Parachute deployment at programmed altitude. The aircraft slowed. The parachute deployed. Perfect timing. The prototype descended gently, landed in grass 200 yards downrange. Minor damage. Repairable. The camera intact. Clarke developed the film that afternoon. 48 frames of clear, sharp imagery. The Ottawa River, surrounding fields, roads, buildings, accurate resolution, usable intelligence, everything a reconnaissance photograph needed to be. He sat alone in the development room, holding the film strip up to light, and wrote a single sentence in his logbook. For the first time, I saw the Earth through an unhuman eye. Not triumph, not celebration, just quiet acknowledgement of what they'd accomplished. A camera that flew without a pilot, a machine that gathered intelligence without risking human life. A promise that maybe, possibly reconnaissance might become less deadly. Cheswick found him an hour later still sitting in the dark room, still holding the film. "We did it," Cheswick said. Clarke looked up. "We proved the concept," he replied. "Now, we need to convince someone it matters." That night, Clarke wrote a new report. Technical specifications, flight data, photographs attached. He titled it Successful Demonstration of Remote Aerial Observation System. He submitted it through official channels, knowing it would probably be dismissed again, knowing bureaucracy moved slower than innovation, knowing the military establishment didn't trust ideas from civilians working in unheated hangars. But he also sent copies to 3 people who might understand. An RCAF intelligence officer stationed at NRC, a British liaison officer visiting Ottawa for radar consultations, a Canadian Army reconnaissance commander who'd lost half his photo interpretation unit at Dieppe. One of them would listen. One of them would see the potential. One of them would recognize that the future of reconnaissance was sitting in Hangar 7, built from scrap and stubbornness, waiting for someone with authority to take it seriously. Clarke walked back to the hangar that evening. The prototype sat on Sawhorse's parachute silk draped across its wings. A machine that had flown without a pilot. A camera that had seen without human eyes. He touched the propeller gently. Tomorrow, he thought, we build another. We keep building until someone pays attention. We keep building until reconnaissance stops requiring coffins. The hangar was dark and cold, but the machine inside represented warmth, hope, the possibility that engineering could reduce the terrible cost of war. Outside stars emerged in the summer sky. Somewhere over Europe, reconnaissance pilots prepared for night missions. Somewhere mothers waited for telegrams. Somewhere the arithmetic of war continued calculating casualties. But in Ottawa, in an unauthorized hangar, a quiet engineer had proven that arithmetic could be changed, that machines could bear risk, that maybe finally seeing the enemy didn't require dying to do it. August 23rd, 1943, 1,400 hours. The same rural airfield near Rockcliffe, but different circumstances. Official observers, military vehicles parked along the grass strip, RCAF officers in pressed uniforms, a British liaison colonel from RAF Bomber Command, 2 photo interpretation specialists from intelligence, an NRC administrator who'd rejected Clarke's proposal 11 months earlier. Reginald Clarke stood beside his 3rd prototype, same basic design as the July test aircraft, refined control systems, improved radio response, strengthened airframe, fresh paint this time, dull gray, almost professional. The aircraft sat on a wheeled dolly, ready for launch camera loaded with fresh film. The RCAF intelligence officer who'd received Clarke's report had made this happen. Wing Commander Arthur Sinclair, 42 years old, lost 3 reconnaissance pilots in 6 weeks. Read Clarke's technical specifications twice, requested a demonstration, called in favors, assembled witnesses who mattered. Clarke was nervous, not about the aircraft. The technology worked. 3 successful flights in July, 2 in August, proven concept. But this audience represented authority. These men controlled budgets, resources, official recognition. If the demonstration failed, Project Owl died permanently. If it succeeded, maybe reconnaissance doctrine changed. The British colonel spoke first. Wing Commander Sinclair tells me you've built a pilotless reconnaissance aircraft, he said, using salvaged parts, without authorization, in your spare time. His tone suggested skepticism. Clarke nodded. Yes, sir, that's accurate. The colonel walked around the prototype slowly, examining construction, checking control surfaces. Touching the camera mount, how much does it weigh, he asked. 68 pounds fully loaded, Clarke replied. Range, 5 miles, maximum current configuration. Altitude ceiling, 3,000 feet. We haven't tested higher, the colonel grunted. Show me it works, he said. Clarke signaled Thomas Bright at the radio transmitter. Bright had practiced this demonstration for 3 days. Every control input memorized, every altitude change calculated, every turn precise. Cheswick started the engine. The propeller caught immediately, perfect idle. Clarke stepped back. Launch when ready, Wing Commander Sinclair said. Bright advanced throttle. The prototype rolled forward, gathered speed, lifted at 42 feet, climbed steadily, reached 200 feet and leveled. The officers watched in silence. The aircraft banked left, smooth turn, banked right, equally controlled, descended to 100 feet, climbed back to 200. Every movement deliberate, precise, unmistakably under radio control. The camera clicked continuously. 16 frames, 32, 48, 64. Clarke had programmed a flight path over the Ottawa River Valley. Specific landmarks, roads, buildings. The same targets he'd photographed in July. He knew what the film would show. He needed these officers to see it. 4 minutes airborne. Bright initiated recovery sequence. The engine throttled back. Parachute deployed at programmed altitude. Perfect timing. The prototype descended gently, landed 200 yards downrange. Minor bounce. Settled. Intact. The officers said nothing. Clarke couldn't read their expressions. Professional poker faces, military training. They walked to the landed aircraft, examined it. The British colonel knelt beside the camera, opened the housing, removed the film canister. This needs developing, he said. How long? 40 minutes, Clarke replied. I can do it at NRC headquarters. The colonel checked his watch. We'll wait, he said. The drive back to NRC took 12 minutes. Clarke's hands shook on the steering wheel. Bright sat beside him. You did perfect, Clarke said quietly. Every input was flawless. Bright exhaled slowly. I thought I'd overcorrected on the second turn. You didn't, Clarke said. It was textbook, the photography lab. Clarke developed the film while 8 military officers waited outside. Standard process, developer, stop bath, fixer, wash. Every step careful, methodical. He'd done this 50 times, never with this much riding on the result. He hung the film strip to dry, turned on the examination light, looked, sharp imagery, clear focus. The Ottawa River visible in perfect detail. Roads accurate within meters, buildings identifiable, trees, fields, shadows indicating time of day. Everything a reconnaissance photograph required. Better than some manned aircraft produced. Sharper than typical high-altitude photography. Usable intelligence. Clarke stepped outside. The film is ready, he said. The officers filed into the examination room. Clarke clipped the film strip to the light box, pointed out details. This frame shows the Eastern Bridge approach. This one captures the rail junction. This sequence demonstrates overlapping coverage suitable for stereoscopic analysis. The camera maintains stability throughout the flight. No vibration blur. No atmospheric distortion. Quality equivalent to standard F-24 reconnaissance photography. The British colonel leaned close to the light box, studied each frame, measured angles with practiced eye. He'd evaluated thousands of reconnaissance photographs. He knew what mattered: resolution, clarity, intelligence value. He straightened, turned to Clarke. How much would it cost to build 10 of these, he asked. Clarke calculated quickly. With proper funding and materials access, $800 per unit. The colonel looked at Wing Commander Sinclair. That's less than replacing one damaged Spitfire, Sinclair said. The colonel nodded. Considerably less than training a replacement pilot. The NRC administrator who'd rejected Clarke's original proposal cleared his throat. The technical specifications are impressive, he admitted, but operational doctrine requires further analysis, integration with existing reconnaissance units, training protocols, recovery procedures. The British colonel cut him off. Doctrine changes when technology demands it, he said. This technology demands it. Wing Commander Sinclair pulled Clarke aside. I'm recommending immediate funding, he said quietly. Small-scale production, field testing with operational units, code name to follow. This isn't experimental anymore. This is operational capability waiting for deployment. The photo interpretation specialists approached Clarke next. Both had reviewed the film strip twice. The older one spoke first. We lose pilots because they fly too high for clear photographs, or too low for survival, he said. Your aircraft flies at the perfect altitude because it doesn't care about flak. That alone justifies development. The younger specialist added, every photograph here is usable intelligence. No wasted missions. No blank film because the pilot had to evade fighters. This represents efficiency we've never achieved with manned reconnaissance. Official report filed August 25, 1943. Technical evaluation of remote aerial observation system. Conclusion. Feasibility proven. Operational potential significant. Recommend further trials under classified designation. Proposed code name, Project Wren. Clarke read the report in Wing Commander Sinclair's office 3 days later. Project Wren, he said. Why, Wren? Sinclair smiled slightly. Small bird, unassuming, easy to overlook. But it sees everything. Seemed appropriate. Funding approved September 1943, $12,000 for prototype development. Access to military-grade components, official workshop space. 2 additional engineers assigned. Clarke could barely process it. 18 months of working in secret, building without permission, risking his career. Now the military was handing him resources and asking him to build more. He stood in the new workshop larger than hangar, 7 heated, properly equipped, and felt the weight of validation. Not triumph, not vindication, just quiet acknowledgement that persistence had mattered, that refusing to accept reconnaissance casualties as inevitable had been correct, that machines could bear risk instead of men. Thomas Bright and Robert Cheswick received official positions on the project, salary, recognition, credit for their contributions. Cheswick grinned when he heard. Guess we don't get fired after all, he said. Clarke shook both their hands. You built this as much as I did, he said. Every hour in that freezing hangar, every salvaged part, this belongs to all of us. Wing Commander Sinclair visited the workshop in October, brought blueprints for proposed modifications, longer range, higher altitude capability, improved camera systems. The RAF wants 6 units for field testing, he said. If they work in operational conditions, full production follows. Clarke looked at the blueprints, saw his basic design expanded, refined, transformed into military equipment. He'd built an eye that risked no man's life. Now that eye would see battlefields, scout enemy positions, guide artillery, save soldiers who'd never know a quiet engineer in Ottawa had cared enough to refuse the arithmetic of war. He touched the blueprint gently. We'll build them, he said, and they'll work. Project Wren never saw combat. 6 prototypes completed by December 1943. Field tested at RCAF Station Trenton through January 1944. Performance exceeded specifications. Range 7 miles. Altitude ceiling 4200 feet. Camera resolution superior to standard reconnaissance photography. Recovery success rate 83%. Every technical metric validated, every operational requirement met, but the war was moving faster than procurement cycles. By February 1944, Allied air superiority over Europe was nearly absolute. Luftwaffe fighter strength declining, flak batteries still dangerous but predictable, reconnaissance casualties dropping. Spitfire PR variants, flying deep penetration missions with acceptable loss rates. The urgent crisis that had driven Clarke's work was resolving through different means. Overwhelming force, industrial production, pilot training programs finally catching up to demand. The operational need for pilotless reconnaissance diminished before Project Wren reached production. March 1944. Wing Commander Sinclair delivered the news personally. Budget reallocated to radar jamming systems, he said. Higher priority for current operations. Your aircraft work perfectly. The timing just doesn't align with strategic requirements. Clarke nodded. He'd expected this. Military necessity drove innovation, but also killed it when circumstances changed. 6 prototypes. 8 months of official development. 18 months of secret work before that. All of it functional, none of it deployed. But someone had been paying attention. A British naval officer named Lieutenant Commander Reginald Denny visited the Project Wren workshop in April 1944. American accent despite the Royal Navy uniform. Former Hollywood actor turned aviation enthusiast. He'd been developing radio-controlled target drones for anti-aircraft gunnery practice since 1940. His company Radioplane supplied the U.S. military with thousands of OQ-2 target aircraft. Denny spent 3 hours examining Clarke's prototypes, asked detailed questions about gyroscopic stabilization, radio frequency selection, camera mounting systems, recovery mechanisms. He took notes in a leather-bound journal. Never asked for blueprints. Didn't need to. The principles were visible in the hardware. Your recovery parachute system is brilliant, Denny said. We've been using net capture. Your method is simpler, more reliable. Clarke showed him the timer mechanism. Altitude-based deployment. Fail-safe in case radio signal lost. Denny nodded slowly. May I suggest something, he said. Document everything. Technical specifications, test results, lessons learned. This war will end. The next one will need this technology. Clarke did exactly that. Between April and August 1944, he wrote comprehensive documentation. Project Wren Technical Manual, 127 pages. Detailed schematics, flight test data, radio frequency tables, material specifications, failure analysis, recovery procedures, everything necessary to recreate his work without starting from scratch. He submitted it to the National Research Council archives. Classified, restricted access. Filed under experimental aircraft systems. Then he went back to radio calibration. The war ended. Clarke returned to civilian life. Took a position with Canadian Marconi Company designing commercial radio equipment. Never spoke publicly about Project Wren. Never claimed credit. Never sought recognition. Colleagues knew him as a quiet engineer who'd done something important during the war but didn't discuss it. He died in 1967. Heart attack. Age 58. Obituary mentioned his work at NRC. 3 sentences, no details. His documentation sat in archives for 22 years, 1,989. NRC historian conducting research on wartime aviation projects stumbled across the Project Wren files, declassified decades earlier but never examined. The historian Dr. Margaret Chen read Clarke's technical manual twice. Then she started connecting dots. British development of radio-controlled target drones in 1944 used recovery systems nearly identical to Clarke's design. American OQ-2 variants introduced in 1945 incorporated gyroscopic stabilization matching his specifications. Post-war reconnaissance drone programs referenced Canadian prototype systems without naming sources. The influence was there, undocumented, unattributed, but unmistakable. Dr. Chen published her findings in the Canadian Journal of Military History. Forgotten Innovators Reginald Clarke and the Origins of Unmanned Reconnaissance, 6 pages. 3 photographs of Project Wren prototypes. Detailed technical analysis, historical context, nobody noticed. Academic journal, limited circulation, specialist readership. The article appeared, generated no response. Clarke remained unknown. Project Wren stayed forgotten. The quiet engineer who'd built Canada's first remotely piloted aircraft remained exactly what he'd always been. Anonymous, unrecognized, lost in the vast machinery of wartime innovation where thousands of brilliant ideas emerged and most disappeared without acknowledgement. But the ideas survived. Cold War drone programs built on principles Clarke had proven. Reconnaissance without risk, observation without pilots, cameras that flew themselves. The technology evolved, became sophisticated, jet-powered, satellite-guided, but the fundamental concept remained unchanged. Machines bearing risk instead of men. Vietnam. American Ryan Firebee drones photographed North Vietnamese positions. No pilots lost. Intelligence gathered continuously. The concept Clarke tested over Ottawa River Valley scaled to combat operations. Thousands of missions, thousands of photographs, zero casualties. Gulf War 1991. Pioneer UAVs provided real-time reconnaissance. Commanders watched enemy positions from command centers hundreds of miles away. The flying eye Clarke envisioned in 1942 became standard equipment. Afghanistan, Iraq, Syria, Predator drones, Reaper drones, Global Hawk Reconnaissance platforms, continuous surveillance, persistent observation. The direct descendants of crude plywood prototypes built in an unheated hangar by a man whose brother died over France. Clarke never knew, never saw his ideas validated on that scale, never witnessed the transformation of warfare his work helped create. He'd wanted to save reconnaissance pilots. He'd proven machines could do the job. That was enough. The rest was history's business, not his. His technical manual remains archived at the National Research Council, available to researchers, rarely requested. The prototypes were scrapped in 1946. Metal recycled, wood burned, only photographs survive. Grainy images of simple aircraft that represented profound innovation. From Clarke's crude plywood wings came the age of the unmanned sky. Not directly, not obviously, but the thread connects, the principle established, the proof delivered. One quiet engineer refusing to accept that reconnaissance required sacrifice. One impossible idea pursued despite rejection. One machine that flew without a pilot and demonstrated that perhaps finally seeing the enemy didn't demand dying to do it. The legacy wasn't fame, it was function. Ideas that worked, concepts that mattered, technology that reduced casualties, even if it took decades to realize its potential. History remembers the pilots who flew, the aces, the heroes, the men whose names appear in books and documentaries. But sometimes the greatest contribution comes from someone who refused to let more names be added to casualty lists. Someone who believed engineering could save lives if given the chance. Someone who built a flying eye in secret and proved that courage wasn't always found in cockpits. Sometimes courage was found in refusing to send anyone into the cockpit at all. Today, drones are eyes in every sky. Predators circle above mountains where soldiers patrol. Reapers track convoys across deserts. Global Hawks photograph continents from altitudes where human pilots cannot survive. The machines see everything, record everything, strike with precision measured in meters. They save lives by providing intelligence that prevents ambushes, locates hostages, maps, enemy positions before troops arrive. They also take lives. Remote pilots sitting in air-conditioned trailers 7,000 miles from target zones, press buttons, and people die. The same technology that Reginald Clarke imagined to protect reconnaissance pilots now delivers missiles through windows. The flying eye he built to observe has become a flying weapon that destroys. Clarke never intended that. He wanted to save his brother. He wanted to stop reconnaissance pilots from disappearing over France. He wanted machines to bear risk so men could live. The moral simplicity of 1942 has become the ethical complexity of the 21st century. Unmanned aircraft eliminate casualties on one side while inflicting them on another. The technology is neutral. The application is not. But the fundamental principle Clarke proved remains true. Observation can be separated from physical presence. Intelligence can be gathered without putting human operators in direct danger. Reconnaissance no longer requires the terrible arithmetic that consumed pilots at 18% monthly loss rates. Modern militaries survey battlefields continuously, persistently, without risking air crews. That part of Clarke's vision succeeded completely. The cost was measured differently than he imagined. He worked in an unheated hangar because young men were dying for photographs. He salvaged parts because bureaucracy moved slower than casualties. He refused official termination orders because rules made in offices seemed less important than lives lost in combat. His motivation was purely humanitarian. Save the pilots, stop the bleeding, build something that made reconnaissance less deadly. History honored that intention by forgetting him entirely. No medals, no recognition during his lifetime. No public acknowledgement that a quiet electrical engineer in Ottawa had helped pioneer unmanned aerial reconnaissance. He died unknown. His obituary mentioned wartime service in 3 sentences. His prototypes were scrapped. His name appeared in one academic journal article read by perhaps 200 specialists. But his brother's name appears on a memorial in Oxfordshire, Flight Lieutenant David Clarke, lost over France February 1941, one of 55573 Bomber Command aircrew killed during World War II. The memorial lists them all, column after column of names. Young men who flew into fire because their missions required physical presence. Reginald Clarke spent 3 years trying to make that list shorter, trying to separate observation from sacrifice, trying to build a machine that could see without bleeding. He succeeded technically. The prototypes worked. The concept was sound. The mathematics proved correct. Whether he succeeded morally depends on what unmanned aircraft became after his death. Whether technology designed to save lives but later used to take them represents success or failure. Whether the humanitarian intent matters when the practical application diverges completely from original purpose. Clarke couldn't answer those questions. He built a flying eye. History decided what that eye would look at and what would happen when it saw. But in November 1942 inches, a freezing hangar, a man whose brother had disappeared over enemy territory, made a choice. He chose to believe engineering could reduce suffering. He chose to build something that might save pilots. He chose persistence over permission, action over acceptance, hope over arithmetic. The sky above us now fills with machines that fly without pilots. Some observe, some strike, some save, some kill. All of them trace lineage back to crude ideas tested by people who believed technology could change the terrible mathematics of war. Reginald Clarke never sought fame. He wanted one thing: to see the world without losing another brother. History remembers the pilots who flew, the aces who scored victories, the crews who survived impossible missions, the names carved into memorials. But sometimes the greatest courage is found in the ones who refused to send anyone up at all, who looked at casualty reports and said no, who believed machines could bear what men should not, who built futures they would never witness from wreckage and stubbornness and grief. The sky is full of their children now, flying eyes, unmanned observers, machines that see without dying. Clarke would recognize the technology. Whether he would recognize the world it created is a different question entirely.